Hello everyone. Today I'm going to present the topic metric representations, homogeneous coordinates, and composite transformations, which is an important concept in computer graphics and computer vision. These concepts explain how computers perform operations such as moving, rotating, scaling, and transforming graphical objects efficiently. Throughout this presentation, we will understand why matrices are used, what homogeneous coordinates are, and how composite transformations improve computational efficiency. Before we begin, let me briefly explain the flow of the presentation. First, I'll introduce the basic concept of geometric transformations. Then, we will discuss matrix representation of points, followed by homogeneous coordinates. After that, we will study different types of transformations like translation, scaling, and rotation. Next, we will understand composite transformations using a numerical example. And finally, we will look at some real world applications and conclude the presentation. Let's start with the introduction. In computer graphics, every object it is represented using coordinates. Whenever we need to move, rotate, resize, or flip any object, we perform these operations, which are called geometric transformations. Instead of changing every coordinate manually, mathematics provide a much simpler solution using matrices. A matrix allows us to perform transformations efficiently through multiplication. However, one problem exists. Normal coordinate systems cannot represent translation using ordinary matrix multiplication. To solve this issue, we introduce homogeneous coordinates, where an extra coordinate is added. And using homogeneous coordinates, every transformation, including translation, can be represented using the same matrix multiplication process. Furthermore, instead of applying multiple transformations one after another, we combine them into a single composite matrix. This reduces computation, improves the performance, and it is widely used in animation, CAD software, CAD software, computer vision, robotics, and game development. Now the question arises, why matrices? Why do we use matrices in computer graphics? As we discussed, matrices are used because they provide a mathematical way to represent transformations. Instead of writing separate equations for every point, we simply multiply the point by a transformation matrix. Another advantage is that multiple transformations can be combined into one matrix. This reduces the number of calculations required. Modern graphics processing units or GPUs are specially designed to perform millions of matrix multiplications every second. This is why graphics applications, video games, and simulations rely heavily on math. Now, let's see how a point is represented. Suppose we have a point P with coordinates x and y. Instead of writing it as an ordered pair, we represent it as a column vector. Whenever we want to transform this point, we multiply it by a transformation matrix. The equation is very simple. The transform point P prime is equal to the transformation matrix M multiplied by the original point P. And almost every transformation in computer graphics follows this same principle. Now, there are five basic two-dimensional transformations which are discussed. The first one is translation, which moves an object from one position to another without changing its size or orientation. Now, the second is scaling, which enlarges or shrinks an object. The third is rotation, which turns the object around a fixed point by a certain angle. The fourth one is reflection, which creates a mirror image of the object. And at last, the fifth is shearing, where the object appears slanted while maintaining parallel side. These five transformations together form the foundation of almost every graphical operations in computer graphics. Now let's understand why homogeneous coordinates are needed. A 2 by 2 matrix can perform scaling, rotation, reflection, and shearing. However, it cannot perform translation because translation requires adding values rather than multiplying. To overcome this limitation, we introduce an additional coordinate. Instead of representing a point as x and y, we represent it as x, y, and 1. This creates a three-dimensional vector called homogeneous coordinate. Now, all transformations, including translation, can be represented using 3 by 3 matrices. This provides a unified mathematical framework for graphics transformation. Let's see how translation is represented. Suppose we want to move an object A units along the x-axis and B units along the y-axis. The translation matrix contains these values in its third column. When this matrix is multiplied with a homogeneous point, the coordinates are shifted accordingly. The object's shape and size remains unchanged, but its position is changed. Only its position is changed. Now let's go to the next type of transformation, which is scaling. Scaling changes the size of an object. The scaling matrix contains two scaling factors. One is Sx and another one is Sy. If these values are greater than 1, the object becomes larger. If they are between 0 and 1, the object becomes smaller. If both values are equal, uniform scaling occurs. And if they are different, the object stretches differently along each axis. So this is about scaling matrix. We will now move on to rotation matrix. Here, rotation, what is rotation? Rotation is a type of transformation technique which changes the orientation of an object. The rotation matrix uses sine and cosine functions of the rotation angle. A positive angle produces an anti-clockwise rotation. A negative angle produces a clockwise rotation. One important property of rotation is that it changes the direction of the object, but not its shape or size. This transformation is widely used in robotics, gaming, and animation. operations separately, we multiply all the transformation matrices together. The resulting matrix is called the composite transformation matrix. One very important point is that the order of multiplication matters. Changing the order produces different results. Therefore, transformation order must always be carefully chosen. As we have shown here in the combined matrix, M equal to T multiplied by S into R. T is translation, S is scaling, and rotation. This order should be followed. Now let's understand this with an example. Suppose the point is 1, 2. First, we scale it by a factor of 2. Then we translate it by 3 units along the x and 1 unit along with the y-axis. Before applying these operations, the point is converted into homogeneous coordinates by adding the third coordinate as 1. In the first step, we apply the scaling matrix. Since the scaling factor is 2 in both directions, every coordinate becomes twice its original value. The point 1, 2 therefore becomes 2, 4. Only the size changes during scaling. The object's position relative to the origin remains same. Next, we apply translation. The scale point 2, 4 is shifted by 3 units in the x direction and 1 unit in the y direction. After adding these values, the final coordinates become 5, 5. This demonstrates how translation changes only the object position. Now, instead of performing scaling and translation separately, we can also combine both matrices into one composite matrix. Now only one matrix multiplication is required. The final result remains exactly the same. This approach is much faster and is used extensively in computer graphics because thousands or even millions of points may need to be transformed in real time. Now, in this figure, there will be a difference between the original object and the transformed object. The original object appears in its initial position. After applying scaling and translation, its size and location changes according to the transformation matrix. Visualizing transformations in this way helps us understand how mathematical operations affect graphical objects. Now let's move on to some of the applications. These concepts have many practical applications. In computer graphics, they are used to render two-dimensional and three-dimensional scenes. In animation, they help move and rotate characters naturally. Camera transformations in gaming and virtual reality also rely on matrices only, and the image processing uses transformations for resizing, rotating, and correcting images. So, in computer graphics, geometric transformations are essential for object tracking, image registration, and feature matching. At last, robotics, augmented reality, autonomous vehicles, and medical imaging all depend on these mathematical concepts. Now, to conclude, matrices provide a simple and efficient way to represent geometric dimensions, and homogeneous coordinates solve the limitation of ordinary matrices by allowing translation through matrix multiplication. And together, these concepts form the mathematical foundation of modern computer graphics, and it helps in animation, computer vision, robotics, and many real world applications. Thank you for this.